all, I'm going to review what are the techniques that one can adopt to study topological properties by lattice simulations. So first of all, we have to face the problem of defining topology on a discrete space-time, which is in some sense, it is a nonsense from a certain point of view. But we have several definitions going from gluonic to fermionic definitions, and I will review renormalization that has to be taken care of when considering topological observables. I will describe you smoothing methods and fermionic methods, and then I will review some determinations of the topological susceptibility which have been obtained at zero temperature. Then I also have a few more slides regarding results going beyond the topological susceptibility. Okay, I don't know if I will manage to cover that today, so it's not in the outline. Maybe it will be in tomorrow's lecture. So, strictly speaking, topology is not well defined on a lattice because we don't have a concept of homotopy. How can we measure an integer winding number on a discrete space-time? One possible idea is to make an interpolation of the discretized fields by continuous fields. Okay, in this way you recover, in some sense, a concept of topology, and this is the idea which is at the basis of the so-called geometric definitions of topological charge on the lattice. Usually they work well if you have smooth enough gauge fields. Okay, nevertheless, I mean, I will show you some examples in the simplified models that we discussed last week of these geometric charges. In any case, even if such definitions are possible, in principle, one should take into account that on a discrete space-time, a strict division into homotopy classes disappears. So what does that mean? It means that in any case, you can move from one topological sector to the other by crossing finite action configurations. So when we are in the continuum, you can imagine that the space of configurations, now what I'm drawing is not, does not make many sense in a space of configurations, but imagine that the space of configurations is just this line. When we are in the continuum, such configurations are divided in topological sectors. So if you here you have the continuum action, and you imagine of dividing the configurations into topological sectors. So say you have here you have topological sector with winding number 0, then you have winding number 1, -1, and so on. These topological sectors are divided by infinite barriers. So the continuum action diverges in some sense at the border of one topological sector, and then you have the other topological sectors, which in each topological sector we have minimum action configurations. Okay, so in some sense instantons are sitting here. Okay, and also here, of course. But I mean, such topological sectors are separated by infinite barriers, which prevent you from going continuously from one topological sector to the other. When you are on the lattice, such barriers, even if you manage to define a sort of interpolation of your fields by such sort of geometric charges, in any case, such barrier disappears and you can continuously move from one sector to the other. So the red picture is what you expect to have on the lattice. Okay, so you can have a continuous crossing between different topological sectors, even if you define such sectors by an interpolation. So how this interpolation works, it is quite clear in the simplified models that we considered. For instance, if you consider the particle on a circle, you can just, I mean, this is a picture of a possible discretized path, and I mean, this is the circle going from 0 to pi r in the notation of the previous lecture, okay? And this is the imaginary time going from 0 to beta times h bar actually. And I mean, this is a possible discretized path with periodic boundary conditions. You can just count how many space you run as you go through the temporal boundary conditions. And for instance, in this case, I mean that you can just, if you draw the path on a circle, you can follow in each segment how many the minimum arc going from one point to the other, okay, and count just the angle that you make, which in this picture is just the horizontal path that you go from one point to the other, okay. And at the end, you will make either a complete round around the circle in discrete steps, okay, or not, or you can make more than one round. But in any case, at the end, you have an integer number of winning, even if the time is discrete in this case, okay? So you just count the minimum arc from one point to the other. And this is a sort of geometric definition. I mean, you are assuming of interpolating between one point and the other by a stepwise function, in a linearly interpolating function, sorry, going from point to the other, which gives you also a possible definition of topological charge. Now, of course, this can be ambiguous if you have 2 points, 2 consecutive points of the path sitting on the opposite sides of the circle. I mean, if you have 2 consecutive points sitting here, it is not well defined whether you go in these directions or in these directions, okay? And this is the case that I drew here. I mean, is this path corresponding to 0 topological charge or to -1 topological charge? I mean, it depends on the way you interpolate, and if they are on the opposite sides of the circle, there is an ambiguity. So this is the sort of ambiguities that you may have when you have geometric definitions of the topological charge interpolating the discretized field. And it is an ambiguity which is present if you have large fluctuations in your path. Now, in one dimension, large fluctuations are not usual, but as you go to larger dimensions, such fluctuations are more usual, and can give ambiguities which come in a larger and larger number. And if you go to the two-dimensional U1 gauge field, so the two-dimensional electromagnetism, you can also in this case give a geometric definition of the topological charge, which is the following. You just take in this case you have U1 gauge link variables going around plaquettes, and you have a phase. I mean, the plaquette can be written, this pi12 can be written as the exponential of a phase, a real phase, where usually this phi12 is taken between -pi and pi, okay, which is the meaning of this arc function. In this case, if you divide the argument of each plaquette by 1 over 2 pi, you are counting exactly the flux going through the plaquette. So since the topological charge in a two-dimensional U1 gauge field is nothing but the total flux going through the lattice, you are in some sense exactly counting the flux of a corresponding interpolating field going through the lattice. And this is integer valued because in any case you are on a compactified discretized lattice, which is a torus. So in any case it is integer valued, but also in this case you can have ambiguities, for instance when the phase of the plaquette is sitting close to pi, okay, and you can when you cross pi you may change Q by 1 unit by continuous change, modification of the gauge fields. Now you can play the same game also in SUN Yang-Mills theory. There are, of course, it's more difficult to write them down, so they are more sophisticated. But in any case, they are well defined, and you can find references here. And they're characterized as the definitions that we have seen in lower dimensions by being non-analytic functions of the gauge fields. Okay, so you can switch from one integer value to the other by just making continuous modifications of the gauge fields. So in this sense, they are expected to be non-analytic. Now, while such definitions can be adopted, in four-dimensional SUN gauge theory is more amenable to make use of standard discretizations, which are more amenable to analytic and numerical treatment. For instance, you can just make a standard gluonic discretization of the topological charge density, which is the following. In this case, I mean, you are just taking the GG dual and discretize it in terms of plaquettes. This is one of the simplest possible definitions. In practice, the operator that you consider is a combination of two plaquettes. You go, you take two plaquettes, and this is the plaquette in the mu nu plane. And you don't close it, so you continue before taking the trace. You also make another round in another plaquette going in the, I mean, this should be rho and sigma directions. And then you take the trace, so you close it. And you can prove that in the naive continuum limit, this operator reproduces GG dual, okay? Now the problem is that this simplified discretization, which is much more simple much simpler than the geometric definition, as the problem is that it is non-integer valued. So it is much simpler than the geometric definition, but as you measure it on a gauge field configuration, it turns out that it is non-integer valued, and that you have to take care of renormalizations, which relate its correlators to the corresponding continuum quantities. So let me make a review of such renormalizations. First of all, you have a multiplicative renormalizations, which relates the discretized version to the continuum charge. And this multiplicative renormalization must be intended in the sense that when you consider correlation functions of the discretized topological charge, you have to take into account a multiplicative renormalization for each power of Q that appears in the correlation function. Okay. Now, when you consider the topological susceptibility, which is the expectation value of Q squared, so you can write it down as the integral of the 2-point function of the topological charge density. you have the appearance of a further renormalization, which is an additive renormalization, which has been usually called M. And this comes from the contact term in the two-point function. Okay, this contact term is singular. Actually, it is singular even in the continuum limit. I mean, if you consider how this two-point function behaves, this two-point function is negative for non-zero distance. Okay, so for x when it is negative when the x and y are different, and that means that since the integral has to be positive, okay, because q squared is a positive definite quantity, it means that this two-point function, I mean, if you make a plot of this two-point function, it is negative, and then it has a delta-like singularity in the origin, okay? So it is singular in the origin, it has a contact term which guarantees that the topological acceptability is a positive quantity. Now, since you have a divergence in the origin, it means that you have a given prescription which reproduces the continuum topological acceptability, and you are not guaranteed that when you consider the lattice discretization of the topological charge density, the same prescription that you have in the continuum is reproduced. So you may expect that you have, apart from the multiplicative renormalizations, which appears in the two-point function, also an additive contribution, which must be subtracted. Okay. In some sense, an heuristic picture that you may have for this gluonic definition, for this simple gluonic definition, is that configuration by configuration, the discretized topological charge is related by a sort of true topological background by a multiplicative renormalization, this Z-mod renormalization, plus some noise, okay, some noise which make it fluctuating around this average value. And this noise is such that when you take the expectation value of QL squared, you have also a further additive normalization, which comes from this noise, from this stochastic noise. And this stochastic noise basically stems from the fluctuations of the gauge field at the ultraviolet scale, which is independent of Q and has zero average. And it is this noise that I named eta in this heuristic relation. Okay, so this is the picture that you have. I mean, when you measure the topological acceptability by gluonic definition, a standard gluonic definition like the like for instance this one, you expect to have both multiplicative and additive renormalization that you have to take care of. Okay. Now, if you adopt a geometric definition, like the one defined in the papers from Luscher or from Phillips and Stone, we have some improvement actually from this. The improvement is that the multiplicative renormalization is 1. Okay, and it is 1 basically because the topological charge with the geometric definition is integer valued. So it cannot be different from 1. I mean, you have quantized values of the topological charge, so the multiplicative renormalization is strictly 1. But what happens is that you can have a non-trivial noise adding to the true topological background. And this noise comes from the ambiguity that you may have in the geometric definitions. I mean, it's the same sort of ambiguity translated to the 4-dimensional gauge configurations that you have in the 1-dimensional model, like in this case. I mean, you have a large fluctuation at some site of the lattice where you have an ambiguity from going from deciding whether you are in the 0 topological sector or in the -1, So a small fluctuations of the field around this configuration may bring you in the trivial topological sector or in a non-trivial topological sector. This is just related to the fluctuations at the ultraviolet scale. So they contribute in some sense to this noise that you have around the true topological background. And so the bottom line is that the geometric definitions do not renormalize multiplicatively, but the additive renormalization is still present, and you have to take care of it. In geometric definitions, these noises usually usually named dislocations. I mean, large fluctuations of the field at the ultraviolet scale that give you some fake topological signal. Okay, but it can be interpreted again in this framework. So, if you want to determine topological acceptability by just using a gluonic definition, you have to perform both an additive and multiplicative renormalizations of this sort. Okay, if you measure the lattice topological acceptability, then you have first to subtract an additive renormalization, and then you have to apply also the multiplicative renormalization. Now the question is whether you can determine safely these renormalizations, and you can perform a perturbative computation. It has been performed in the literature at some order in perturbation theory, but actually what you need is a non-perturbative determinations of the renormalization constant. This can be performed in, I mean, there are some heuristic definitions of these subtractions. One possible idea is to prepare a sample of gauge configurations where you know what is the underlying background, so you know what is the topological background from some other method, and then you thermalize the short range fluctuations which are responsible of the normalizations. And in this way, if you measure the lattice topological charge on these configurations, you get an estimate of the multiplicative renormalization. And if you measure QL squared, you get an estimate also of the additive renormalization. I mean, this method works in some sense. I will show you later some results also obtained by this method. But the consideration is that this method relies, in any case, on some other method which defines what is the true topological background Q. I mean, by definition, I mean, you are defining the renormalization constant by measuring, for instance, what is the average value of the lattice topological charge on a set of configurations that have a well-definite topological background Q. I mean, you need to have some other method, which can be another definition of a topological charge, by which you decide what is the value of the underlying topological background Q. So the question is, if you have this other method, why should you bother with renormalizations? Why don't you just compute the cumulants of this well-defined topological charge directly? Okay, so this is the reason why this method, which is based on the renormalization of a gluonic definition, has been used in the past. Actually, I used it during my PhD thesis. But then, in the last few years, smoothing methods or fermionic definitions are more used. Do you have any question at this point?
Yeah, sorry.
Please.
Well, first one about the beginning. So when you did the picture with the action, the continuous action and the configuration, you said there's an infinite well between topological charges. So here, so this means that so in the continuum we either are, so in a continuum setting with boundary conditions where we can define a topological charge, we're either in one or in another of these wells, right? There's...
Yes, exactly. You can imagine of deforming a gauge field, but if you try to change topological sector, in some sense you have to cut the gauge field in some point, so to change the winding number, and in this way you go through some infinite action configuration.
Okay, what do you mean by cutting a gauge field? Sorry.
Well, imagine that.
Does that make? I mean, can that be done in some sense, or?
I mean that you have to go through a discontinuous field.
Okay.
Okay. For instance, imagine of the quantum mechanical example. I mean, you have in that case you have in the topology is how many times the path goes around the circle. Okay, so this is for instance a topological charge 1 path going one time around the circle. So you imagine you want to deform this path, making it trivial. You cannot deform continuously, avoiding this winding number. What we have to do is just to cut the path at some point. So now we have a path which is like this, and then you can make it trivial. But if you pretend it to be continuous, so the action to be finite, then you cannot change the winding number. That's what I mean. I mean, you can, maybe it is more, if I draw it in the two-dimensional torus with periodic boundary conditions, if you have a path which winds once around the lattice, if you perform a continuous modification of this path, you will ever stay with a non-trivial winding number. The only way is to make a cut here, so you make a discontinuity here, and at this point you can change this path and maybe reconnect it in a continuous way. I mean,
okay, sure, but I mean, my intuition about the path integral is that one has to sum over all configurations. So I'm uncertain, even in a continuum, in a continuum setting, whether all the different charges one has to sum over. I mean, over all different configurations, so all topological charges, right?
yeah.
Okay. Yes, thank you.
I mean, also in the continuum, you have these continuous paths which you are summing over, but they have infinite action, so they are suppressed. Okay.
Okay, so the problem of being in one topological sector is just a practical problem, because in theory one has to sum over all topological sectors in the path integral.
Well, that was sum over all topological sector and over all configurations. So
exactly,
that means we are summing also over discontinuous configurations, but they are suppressed. This is exactly the meaning of this divergence here. I mean, in order to go in the continuum from one topological sector to the other, you have to go through an infinite action configuration. And these configurations are are infinitely suppressed in the path integral, in the continuum path integral. They are not suppressed in the lattice discretization of the path integral. Okay, I mean, if you consider now the discretized path, suppose you are in this, you have the following path. Okay, so these 2 points are exactly opposite to each other on the circle. So as you make the interpolation, okay, in order to decide what is the interpolation that you use to define the winding number, you can make either this way, or this way, okay? And you will obtain a difference in the topological charge by 1 unity, okay? So in some sense, this configuration with 2 points sitting opposite to each other on the circle are what I mean for a configuration which on the lattice sits at the boundary here, okay? And on the lattice, in discretized space-time, this configuration has a finite action. Okay, it is not an infinite action, so it has a finite weight in the path integral, so it counts. It is not suppressed. Okay, so you can tunnel from one sector to the other with finite action configuration. But now, as you go to the continuum limit, so this lattice spacing A goes to 0, that will become a discontinuity in the continuum limit, giving rise to an infinite action, which is this barrier which grows as at goes to 0. Okay, is it clear now?
Yes, I think so. Thank you.
Okay. More questions? Now, an alternative way of defining the topological background is to make use of smoothing methods. So what is the general idea of a smoothing method? The idea is to perform a process of local minimization of the gauge action. And so in this process of local minimization, what happens is that the fluctuations at the ultraviolet scale are killed first, and then progressively, as an diffusive process, you kill the fluctuations on larger and larger scales. So in general, this process works because you are dumping out fluctuations up to a given scale, which is a sort of smoothing radius. In this way, since renormalizations are associated with fluctuations at the ultraviolet scales or at the scale of your lattice spacing, you first remove renormalization while you preserve physical correlations, which are above the smoothing scale. Now, this is how it works in general when you are measuring a two-point function of some operator. Okay, you can perform this local minimization of the action, which kills fluctuations at the ultraviolet scale, and in this way you can remove renormalizations. Now, when you apply this to topology, the rationale is less trivial than that, and the reason is that when you consider the q squared, the expectation value of q squared, it is actually an integral over the two-point function of the topological charge density over all distances. Okay, if I go back to this expression here, I mean, if you write the capital Q as the integral of the topological charge density, so you end up with this integral of the two-point function, and this is an integral over all possible distances, all possible values of x minus y. Okay, so that includes also the contact term, which is also relevant for continuum physics. So the way smoothing methods work in topology is actually strictly related to the fact that the topological charge reaches a minimum on classical configurations, which are the instanton configurations. So in some sense, the local minimization process preserves Q. I mean, you stay within a topological sector. I can go back to the slide we were discussing before. You can imagine now this smoothing process of local minimization of the action as taking your configuration on some point here, and then by minimization, it brings it to the to the sort of the minimum. Of course, you may have still ambiguities if you are sitting somewhere, but this regards short range fluctuations, so which are not interesting for the whole topological background. But once you are in a well-defined topological sector, the local minimization process will usually keep you in the same sector. So, in some sense, topology is stable, or at least metastable, if you apply this smoothing procedure. So, this is basically why the method works for topology. And now there are several smoothing procedures which are available, like the gradient flow, or cooling, or stout smearing, and so on. Now, the important thing is that all of them are equivalent. Some of them are cheaper than the other. For instance, cooling is much cheaper than the gradient flow, but the gradient flow is better suited for particular purposes because it is a continuous process. So let me briefly review how these smoothing procedures work. For instance, the gradient flow, which is also known as the Wilson flow when you apply it to the plaquette action. So the idea is to write down a differential equation for the gauge field variables. Okay, a differential equation which corresponds to moving the gauge configurations in the direction of the gradient of the pure gauge action. So the pure gauge action is the plaquette action, for instance, as the following expression. Okay, 2n over ρ0 squared times the sum over all plaquettes. Okay, now you just write a differential equation in a fictitious time, which is the flow time here, this tau here, which is defined by, in this way. I mean, you differentiate by you multiply the link variable by the gradient of the action. Okay, so you take the derivative of the action in this way, and the link derivative of the action can be expressed. I mean, I will not discuss into details how this expression is derived, but finally you end up with the following expression for the link derivative of the action, which gives you how the link must be changed as a function of tau in order to move the configurations along the gradient of the gauge action. And you can prove that the gauge action in this way is a monotonically decreasing function of the flow time. Okay, it can be proved exactly. Another possibility, which is in some sense equivalent, in this case you are continuously modifying the gauge fields by moving towards the minimum of the gauge action. You can do it, and this has been this gradient flow has been proposed and defined for the first time around 10 years ago. There is another technique which has been proposed almost 40 years ago, which is known as cooling. When it was proposed first in the nonlinear sigma model in 2 dimensions by Berg, and then for gauge theories by Tepper in the 80s. The idea is the same, basically, but the minimization process is performed iteratively, link variable by link variable. So basically, you perform a sweep over the whole lattice, in which at each step, each link variable is substituted. So you have the link variable at site x in the direction mu, which is substituted by a new link variable, which minimizes the action. I mean, it maximizes the trace of the action times the staple. Okay, sorry, there is a trace missing here. So this W mu is the staple going around the link. So it's the sum over all the staples, which is the same quantity which appears in the gradient flow. Okay, this W mu, which is nothing but the sum over all the staples around the given link. And now in the cooling process, the new link variable is chosen so as to minimize locally the action. So in some sense, this process minimizes the action by definition, okay, because you look for the minimum gauge link variable over each site. Now the process is, can be written exactly for SU2 gauge group. I mean, the minimum of the trace is nothing but the staple itself divided by the square root of the determinant of the staple matrix. And you can extend this to SUN by just a Cabibbo-Marinari algorithm where you minimize over all the SU2 subgroups. Okay. One important point is that this is an iterative process. That means that I mean, as you cool one link, you may have already cooled down some link variables sitting nearby. Okay, so each link is cooled step by step, and in this way, the action minimization is forced by construction. Now, these are just two examples of smoothing and cooling, and okay. Let me first show you this plot. This is a plot showing how the topological charge evolves, both for using cooling and the Wilson flow on a typical configuration. This is a typical configuration, SU3 configurations. SU3 configuration, and you can see that the topological charge there is a very long plateau in terms of cooling steps or in terms of an equivalent amount of Wilson flow time, over which the topological charge is stable, and it is stable around the value which is more or less 1. So what happened in this case is that basically you, going back to this picture, you are minimizing the action, so you are moving towards the minimum, and you are staying here in a configuration which is metastable. Now, the process is metastable in the sense that since you are on the lattice, you will always find a path to move through another topological sector. This is what happens in this particular case. I mean, if you wait long enough, after order of 1,000 cooling sweeps over the lattice, then you change topological sector finally, and you switch to the trivial topological sector. But you have a very large plateau where the topological sector is stable and where you can define a topological background. And cooling and the Wilson flow work equally well in this respect. Now, there have been several studies checking the equivalence between different smoothing methods, so in particular between cooling and the gradient flow. This is one example. I mean, first of all, you have to match how the number of cooling sweeps that you perform, the local minimization steps that you perform by cooling, correspond to the flow time that you have in the gradient flow. And once you have done that, you can exactly compare. This is the topological charge distribution that you get after smoothing, and this is a comparison between cooling and the Wilson flow. So let me make a zoom of this picture. So basically you can see that there is no difference between the two definitions. I mean, you can see they are hardly distinguishable. if you, of course, if you match the amount of cooling and of Wilson flow that you perform. And as you can see, even after smoothing, you don't have a exactly quantized topological charge. I mean, what you observe are peaks of the topological charge distributions, but the peaks are very well defined. So in some sense, you can associate a corresponding topological sector to each configuration, and we will associate a trivial topological sector to all the configurations sitting in this peak. A topological charge 1 to the first peak on the right, -1 to the first peak on the left, and so on. I mean, in some sense, it is not exactly quantized, but you can quantize afterwards by associating an integer number to each of the peaks that you observe. Okay. So the matching of the topological distribution is perfect for different smoothing methods. Actually, what it is found is that there is an exact correspondence between the number of cooling steps and the Wilson flow time, which is this factor 3, which can be also computed perturbatively. I mean, I refer to this paper for the details. And you can assign an integer number by this histogram peak assignment. And if you look configuration by configuration, cooling and the gradient flow disagree on only 1% of the configurations at this value of the inverse gauge coupling, which is beta 6.2. So the systematic uncertainties is very well under control. And this is how the topological susceptibility behaves as a function of the, for instance, of the Wilson flow time for different values of beta. And you can see that the topological susceptibility has a very well-defined and extended plateau, where it is basically independent of the smoothing, amount of smoothing that you perform. And this is better and better defined as you go towards the continuum limit. For instance, for beta 6.2, basically the function is flat. Okay, so you can take a measure of topological susceptibility at any flow time. And also you can appreciate here that the dependence on the lattice spacing, I mean, these different beta values correspond to different values of the lattice spacing. So the dependence on the lattice spacing is very mild. So we expect that lattice artifacts and finite lattice spacing corrections to be very small. Do you have a question on this?
Yes, maybe one question.
Please.
2 slides before this, when you show the plateau.
Yeah.
Yes. So, no, the one before.
Yeah.
Yes, this one. So here, whichever configuration we start from, we have essentially lost information about that. So let's say I had an educated guess about a finite action configuration on a lattice, then I gauge cool, and then I reach the first plateau, and then I reach the second plateau. So essentially, I found 2 configurations sitting at 2 different minima, but they're not really, they don't have memory of the configuration. I've lost that, right? I mean, I found new configurations which happen to be at the 2 minima.
No, okay. If you perform a small amount of smoothing, of course you can have ambiguities in the first steps of smoothing. I mean, it can happen that you switch from one topological sector to the other. But then the important point is that there is this wide region where the topological charge is stable. Okay. Of course, I mean, this is the what we are measuring here is the topological charge defined by the standard gluonic definition. So let me go to one of the first slides. Here, the quantity which is measured in that plot is just this gluonic definition, okay, which usually renormalizes and it is non-integer valued. But this is measured now over the smoothed configuration, okay? Okay. So as the times go on along the horizontal axis, I'm integrating these flow equations, which move the configuration towards a minimum of the pure gauge action, or equivalently, I'm performing this local minimization process, which changes the gauge link variables step by step by going towards the local minimum of the action. And what happens is that I didn't plot the plaquette action, okay, in this case, but the plaquette action basically goes to zero rapidly, or very close to zero, because you are minimizing it, the density, the action density, of course. And at the same time, the topological charge moves. I mean, in the first steps of smoothing, it may have an unstable behavior, okay, because you are killing the ultraviolet fluctuations, and that will make the charge move quite rapidly. But then you reach this sort of plateau, which means that we have reached an almost a local minimum of the discretized actions. You are sitting in some sense around one of these minima, okay, which defines a well-defined topological background of the configuration. So well, it is defined. It can be read in. If you look at configuration by configuration, you may have that the topological background changes after a while. But if you look at the average quantities, okay, at the average quantities, you can see that the average values of Q squared is practically independent of the smoothing time, and this is better and better visible as you are close to the continuum limit. I mean, here I'm increasing the value of beta, and that means that you are reaching the continuum limit. And you can see it also from the point of view of the action density. I mean, in this plot, which is on the left, on the horizontal axis, we have -1, 1 minus the average plaquette, which means that on the left, you are moving towards a zero action. And you can see that also in this case, I mean, you are minimizing the action, and topological susceptibility is more or less stable. I mean, it's reaching a finite value, which is corresponds to this plateau. Okay. Okay. More questions?
So still concerning this plateau plot here.
Yeah.
So basically, when we continue to, I mean, conceptually speaking, it's clear to me that when I continue to flow or cool and dump this this configuration, at the end I will reach not the local minimum, but like the total minimum of the action. So I will go back in the Q equals 0 sector, basically in the naive sector. But to do so, I still have to. I mean, even in the lattice, I still have to go through not a wall, but not a barrier, but still I have to increase locally. I mean, if you go to your picture.
Okay, no, that picture is actually, I mean, the picture has a problem. The problem is that it is one-dimensional. So it is the picture that this picture.
Yeah, exactly. This picture
is fake. Okay.
Okay.
It's fake because it is one-dimensional. I mean, the space of configurations is much less trivial than this.
Yeah.
So we are around a minimum on a sort of minimum. This minimum is metastable in a lattice configuration. That means that you have sort of escape directions where you can move away from the metastable minimum. So in this sense, it is a naive picture.
Okay. So so basically, you just have to be lucky enough to take the right direction to go down and through, and not through a barrier, and goes to the total minimum, basically.
Exactly. Essentially, in the real configuration, the number of directions is very large. Okay, it's not just one dimension, but it is not infinite, but a very large amount of directions that characterize each configuration. And among such directions, you always find maybe a very narrow path, which brings you towards a new minimum. Okay. But the configuration is metastable, and the important point is that as you reach the continuum limit, this narrow path becomes narrower and narrower, so that finally you end up with a real minimum.
Sure.
Now the point, maybe one point which is worth stressing is that the whole process works because you have a separation of scales. Okay, so as you smooth the configurations, you are basically killing the physical signals over larger and larger scales. Now, what is the point? The point is that the renormalization, which affect the gluonic definition, are basically stem from gauge field fluctuations at the ultraviolet scale, while the typical physical fluctuations, which are associated with a non-trivial topology, live on a physical scale. Now, when you go to the continuum limit, these two scales are well separated. And that means basically that you can eliminate the ultraviolet fluctuations, and this plateau is better and better defined. So we expect that the whole procedure become exact in the continuum limit. And you may expect to have some systematics as you approach the continuum limit, which you will be able to eliminate if you perform a proper continuum extrapolation of your results. Okay.
Okay, thanks.
Now, let me go to the fermionic definitions. The fermionic definitions basically are based on the index theorem, okay, which tells you that you can just count the number of zero modes of the Dirac operator, and then count the number of left-handed zero modes, the number of right-handed zero modes, and subtract them. And it is equivalent to taking the trace of the gamma 5 operator. Now, this method, in principle, works if you are dealing with an exact or an almost exact Dirac operator, which has good chiral properties. An example is the overlap operator, okay, where you have well-defined zero modes with a well-defined chirality, and indeed the overlap operator has been used to measure the topological susceptibility in this way. Now, of course, the problem is that the overlap operator is very expensive. I mean, defining the overlap operator on the lattice is very expensive. I do not have time to review the definition of the overlap operator, but I mean, it is an operator, a Dirac discretization of the Dirac operator, which basically satisfies the Giscard-Wilson relation. So it gives you the best possible operator with the best possible chiral properties while avoiding the doubling problem on the lattice. Now, the question is if you can use also other discretizations like that provided by Wilson fermions or staggered fermions, and make use of the index theorem in any case to obtain a definition of the topological charge. Now the answer is yes, but you discover that in this case you have to take into account the same sort of renormalizations that you had in the gluonic case. So, for instance, you can write down, you have your discretization of your fermions, so you have a definition of gamma 5, and so you can define a sort of discretized topological charge as the trace of gamma 5 in your discretized fermions. Now, what you learn is that this is affected by a multiplicative renormalization, just like the gluonic definition. And this multiplicative renormalization has been studied a long time ago in the 80s, both for Wilson fermions. We have this relation which relates in some sense the correct definition of topological charge to this naive one, and it has a multiplicative renormalization which is related. It can be proven by working with the chiral word identities on the lattice. It is related to the renormalization constant of the scalar and pseudo-scalar non-singlet operator. Okay, so the non-singlet means that, for instance, for the scalar one, you consider all the operators like psi bar, psi j, with ij in different flavor sectors. So this is the meaning of non-singlet. How operators of this kind are normalized. And you can play the same with the pseudo-scalar, so inserting gamma 5 inside. And the renormalization constant of this kind of operators are related to the renormalization of the topological charge defined as trace of gamma 5 by this relation. And a similar relation has been written down by Smith and Bink in the 80s for the staggered operator. So also for staggered fermions, you can define a naive definition of topological charge as the trace of the staggered gamma 5. I mean the staggered gamma 5, I mean the operator which is gamma 5 times the identity, so it has a non-trivial structure in terms of the gauge link variables. I mean, if you have experience with staggered fermions, this is a non-trivial operator which is a non-trivial function of the gauge links, this, in contrast with the gamma 5 with Wilson fermions. So you can take the trace of this gamma 5, and also in this case you have a multiplicative renormalization, which is as the following expression. Now in this case the renormalization constant that appears here are the ones related to the pseudo-scalar and the scalar renormalization in the singlet sector of the staggered fermions. Now, if you just take this definition, even with this multiplicative renormalization, and you trivially define, naively define a topological acceptability by taking the square of these definitions, okay, and measuring average value, you discover that also in this case you have to deal with a additive renormalization, just because of the contact terms that you have also in the gluonic definition. Okay, so basically everything works as with the gluonic definition. Now the point is that in this case you have a nice way to avoid this additive renormalization, so to avoid the contact terms stemming from the two-point function, and this is the so-called method of spectral projectors. So basically the idea is that when you take the square of the topological charge defined in this way, when you take the trace, as in the continuum definition, I mean, last week when we talked about this trace of gamma phi, we explained that this trace of gamma phi is nothing but can be written as the sum over all the eigenvectors of the Dirac operator in this way. Okay, and in the continuum, you can prove that just lambda equal to 0 contribute to this sum. Okay, because when lambda is different from 0, the contribution is exactly 0 by the properties of non-zero eigenvalues of the continuum Dirac operator. Now, when you write down the trace of gamma 5 on the lattice, you can write it also as a sum over the eigenvectors of the Dirac operator, of the discretized Dirac operator. And now the idea is that you don't have to sum over all the eigenvectors. I mean, the additive renormalization comes from fluctuations at the ultraviolet scale. Now, if you cut off the eigenvectors with high eigenvalues, which are associated with the eigenmodes of the Dirac operator at the ultraviolet scale, now we are effectively cutting away the ultraviolet fluctuations contributing to these possible additive normalizations. And this is the idea at the basis of the spectral projectors method, which has been defined for Wilson fermions. I mean, the final expression for the chiral, for the topological susceptibility in this method is the following. And here, this projector is basically a projector which projects over the eigenmodes of the Dirac operator, which have eigenvalue less than a given parameter n, which is a sort of cutoff mass that you insert in the method. Okay, and basically this trace gamma 5 over this projector is something like taking this trace but summing over lambda less than this cutoff mass m. Okay, and the other contributions come from the renormalization factors. So it has been proved in this paper that if you take the continuum limit with a fixed value of the cutoff mass in physical units, then we expect that this definition of the topological susceptibility has cutoff effects which are expected to be of the order of a squared, where a is the lattice spacing. So it's expected to have a well-defined continuum limit, okay, with the cutoff effects under control. And basically, again, the idea is that you are cutting away the high frequency eigenvectors of the Dirac operator, which are related to these contact terms in the two-point function. Now, this can be extended also to staggered fermions, and this has been done last year in this paper. I would like to stress that this idea of cutting away the highest part of the Dirac spectrum is also the basis of a different definition of cooling, which has been proposed almost 20 years ago, in which the idea was to perform a sort of smoothing by just taking into account the lowest lying part of the Dirac spectrum. I mean, if you are interested, I would suggest also to have to read these papers. The proposal was by Christoph Gattringer. Okay, fine. Do you have any questions? So basically, I finished my review of the possible methods that you can use to define and to measure topology on the lattice. Now, what I would like to discuss now is how these methods work. So this picture that I show here, I mean, I produced it on purpose for this lecture. I mean, I made an exercise. I've taken, basically, in my review, I discussed several different methods to define the topological susceptibility on the lattice. The method number one, I mean, you adopt a gluonic definition, and then you take care of renormalizations by measuring the additive and multiplicative renormalization. This is the first method that I discussed today. Then you can adopt cooling or the Wilson flow in order to smooth the gauge fields and define a topological background by a gluonic operator. Or you can use fermionic definitions. So if you use an overlap fermions that you have an exact chiral symmetry, you can just determine the zero modes of the operator and their chirality. Or even if you are using non-improved fermions like Wilson or staggered, you can adopt the method of spectral projectors. So take care of renormalization and obtain a well-defined topological susceptibility with a well-defined continuum limit. Now, the question is how these methods compare to each other. So the exercise that I've done is to take in some sense, the latest determinations from each method in the literature and compare them. And compare them in order to see if they are compatible with each other for the SU3 pure gauge theory. Okay, this is a sort of literature average and average over different methods. And of course, if everything is consistent, even coming from different methods, it means that lattice QCD simulations are able to determine topological susceptibility with accuracy and control over systematic effects, and control over also the continuum limit. So, as you can see, the agreement is good, but one should take care that, I mean, I had to work a bit on some results. For instance, now, I mean, the agreement is that we have 6 determinations, and I reported everything in the same physical units, I mean, in units of the Sommer parameter. Okay, and the Sommer parameter here has been taken for all the determinations from the Sommer paper in the 14th, so in some sense it is reliable. It's a Sommer parameter from Rainer Sommer. And I tried to fit all the determinations to a constant, and the chi-square is 5/5, the reduced chi-square. So it means that these determinations are actually consistent with each other. And in the same plot, I also reported this horizontal line, which is the Witten-Veneziano prediction, okay, which is 180 MeV to the 4th. So this is the the fourth root of the topological restrictibility, actually, okay, which I'm reporting in this plot. And here on the horizontal axis, 1, 2, 3, 4, 5, 6 refer to the 6 different methods that I discussed before, okay? And the corresponding reference from which the determination is taken is reported here on the for each determination, okay? Now, it is important to stress that this comparison works well if you compare results which are continuum extrapolated and also expressed in the same, adopting the same lattice scale. I mean, you should be careful. And indeed, I had to work a bit because the first determination, this one which is associated with the subtraction of renormalizations, actually was a determination which was present in my PhD thesis. Okay, so when I first took the numbers and the determination which was reported in the paper, and I tried to put it on this plot, at the first try, I got a number which was around here, so below, slightly below 180 MeV, and it was not consistent with the other determinations. And so, of course, it was an old determination. It was more than 20 years ago, so maybe it was not precise enough. But then, since I mean, I had all the data because it was my PhD thesis, I went back to the data, and I noticed that there was no continuum extrapolation. So I had 3 values of the lattice spacing, so I could try the continuum extrapolation, and it was not rescaled by the same units. I mean, it was expressed in MEV, but using a determination of the critical temperature of instead of the Sommer parameter. So you have a systematics. If you're using different determination of the scale, you may have some systematics. So I made the exercise of rescaling everything by R0 and performing a continuum extrapolation, and this is the result that I got. Now. I mean, which, as you can see, is consistent with all other results, and gives us this overall agreement, which tells us that the way we determine topological properties by lattice QCD simulations is well under control. Well under control once we perform a proper continuum extrapolation of the results. Do you have any questions?
Maybe just a curiosity.
Yeah.
This last method, spectral projectors for staggered, that seems to have a bit of a big error bar, maybe. Is that because of, do you have an intuitive idea of why, or was it simply?
Yeah, okay. It is quite simple because the purpose of this paper was just to define the spectral projector method for staggered fermions. So we didn't spend much efforts in statistics. Okay, the main purpose was to have a definition of the method for staggered fermions, with the main purpose of using it for dynamical fermion simulations. So the determination was just a numerical check that everything was working correctly. So this is why the error bar is so large. It's not something which is strictly related. I mean, it can be improved. I mean, if you take more statistics and spend more time with performing another value of the lattice spacing, this value can be improved, and for sure. Okay.
Okay, thank you. But do you have an idea whether this could be competitive with other more precise results? I'm looking at like 3 or 4 as in precision, or is there some limitation?
The limitation is now in this case, of course, when you consider pure gauge simulations, the Monte Carlo updating of the gauge configurations is quite cheap. And you just use a hit-but algorithm. So the Monte Carlo, if you make a comparison of the numerical efforts that you have to spend in producing the gauge configurations, the production procedure is quite cheap, because you have a standard algorithm which works quite well. So for pure gauge simulations, the time that you spend in measuring the observable can be significant. I mean, can be relevant to the overall overall estimate of your CPU budget time, time estimate. So in this respect, I mean, if you the different methods have different impact on this. For instance, of course, fermionic definitions have to deal with the measure of the eigenvectors of the Dirac operator, so they are more expensive from this point of view. And so the measure itself can become the most expensive part of the numerical simulation in this case. While, for instance, the cheapest method of all is cooling, okay, because also the Wilson flow, but the Wilson flow, you have to integrate differential equations. So in some sense it is better because it is a continuous sort of continuous cooling, while the standard cooling goes step by step, so it is much faster and cheaper. And this is the reason why you can see here that the well, basically the cooling and the Wilson flow have the smallest errors overall. Also, the overlap fermions have a quite small error, and in that case, I think that the reason is because of large statistics that the authors used at that time. Okay, but I mean, I think that given that all methods are give compatible results, a gluonic definition is, of course, requires less time, so it is preferable. You have more questions? Okay, so it is interesting to now the results that I showed you are for SU3 pure gauge theory, and you can see that I mean, basically they if we go back to the Witten-Veneziano mechanism for the mass of the eta prime meson, they basically confirm this scenario. I mean that the topological settability for the pure gauge theory is more or less of the order of 180 MeV to the fourth. Okay, actually it is a bit higher, but you should take into account that the Witten-Veneziano mechanism works is a large n limit mechanism, so you don't expect to obtain the precise value for SU3. But what is important is that the main important thing is that in order for the mechanisms to work, you need to have a finite value of the topological settability, even in the large n limit. So it is a non-trivial check to see how the topological settability changes as you change the number of colors, and this is the result that is reported in this other plot. Now let me say that in this case, when the values of n which are reported are 4 and 6. So, and this is a plot which is made against 1 over n squared, which is an expansion variable in the 1 over n expansion. So basically, this zero value here is the infinite n limit. And you can see that clearly the result approach a finite value, which seems to approach more and more this 180 MeVs. Also in this case, I've taken I've reported the data not in the same units in which they are reported in the original paper, which is reported here, which were reported in units of the string tension, but I reported them on the same scale of the previous plot, so in terms of the Sommer parameter. But of course, we have to assume that the Sommer parameter has the same at the same value in physical units as for n equal 3. So you can see that the approach is smooth. So these results prove that indeed the topological susceptibility has a finite large n limit, which is also consistent with the Witten-Veneziano mechanism. Now, going back to the previous considerations about which method one should use, let me say that, of course, when you go into large n, so we consider n larger than 1, adopting a fermionic definition can be very, very difficult. So a gluonic definition can be extended trivially to large n, while a fermionic definition would require to define a Dirac operator for SUN, and this is highly non-trivial. While a gluonic definition can be simply extended by, this operator that I brought in the one of the first slides, these definitions of the topological charge, is actually written for any value of n, of the number of colors. So you can trivially extend this, and also everything regarding smoothing here can be trivially extended to it is already written for generic values of the number of colors. So what we learn in the bottom line is that from SU3, sorry, I went a few slides beyond. From SU3, we learned that all methods give consistent results. So you can choose your preferred method or the most convenient method to determine topology. And as you go to larger n, the best method is cooling or the gradient flow. But cooling is cheaper. And so this is the method which has been used for this determination, but we are confident that these determinations, in these determinations also for n equal 4 and 6, systematic errors are well under control because we verified this for SU3. Okay, fine. I think this is a good point to stop the lecture, and tomorrow I will continue and discuss how you determine the further terms in the expansion of the free energy density in terms of theta, so the further coefficients, but we will go to that tomorrow. Now I stop, and if you have questions, of course you are welcome.
Thank you, Massimo.
Can I ask a question?
Yeah, sure.
It's about the first part of the lecture, actually. And I was thinking, if I have a lattice with periodic boundary conditions, then I will have the topology of a torus. And I was thinking, so if I think about the torus as the product of two circles, I can have two plaquettes that go along the two different circles, and so these two plaquettes cannot be deformed into each other. So I was wondering, does this correspond to two different topological sectors?
Well, actually, for the two-dimensional torus, for the, I don't know if you refer to this two-dimensional U1 gauge field.
More generally, so I'm thinking about 2 dimensions because my mind do that, and but then I wasn't really referring to the U1 case. Like in general, I'm building a plaquette on this torus, and I can build one along one circle, and I can build another one along the sort of perpendicular circle. And I was wondering if the fact that I cannot deform these 2 plaquettes into each other correspond to different topological sectors, and then to the fact that I cannot, like the 2 actions will be there will not be like there will be some sort of barrier between them. And I'm not thinking about discretized spacetime now, because of course you say that if we have
But okay, but what you are thinking? You're thinking of the topology of the torus itself, right?
Yeah.
In fact, that on the torus you can have these 2 circles, which the torus is S1 times S1, so it is the product of 2 circles, and it has a well-defined topology. It has a hole, but in this case we are in this case the topology is referred to the topology of the functions which go from the torus to the gauge group. Okay, so it depends on the field that you have on the torus. For instance, if on the torus you put SUN gauge fields, then the topology in that case is trivial, because you can even if you are on the torus but you map it to SUN gauge field, you can always deform the gauge field and make it homotopically equivalent to the trivial configuration, because the gauge group space is large enough. You can unwind the field. Why you cannot do it if you have a U1 gauge field on the torus? So, the topology of the torus itself is not enough to define what is the topology of the configuration space defined on the torus, because it depends strictly on the field that you are defining.
Okay, yeah, I was definitely confusing the 2 things. So if I have a U1 gauge field, for example, like, was that correct, the picture of the 2 plaquettes that corresponds to different topological sectors, or is that still sort of wrong?
Yeah, so basically you have the, oh, sorry. So basically you have to, I'm not able to to make pictures of torus. So basically you have the torus and well, in that case, the best picture to have for topology is the fact that the magnetic flux is quantized. So the magnetic flux that has to go through the torus. I didn't understand what you mean by the plaquette associated with the circle, because actually a plaquette in the case of the torus is just also in that case a loop which has a trivial winding on the top.
Can I do do a path of link that goes around?
Yeah, this is a sort of a Polyakov loop on the torus, a sort of Wilson line.
Okay, and there will be this, like, I cannot deform one into each other's if I draw them properly, right? Yeah.
Yeah,
Yes.
you can deform it. Yeah, exactly. Yes.
So does that mean that these two configurations will correspond to different topological sectors or not?
Well, I mean, it depends on the value that the gauge field takes on over this circle. I mean, again, the topology in the meaning that we are considering here is the topology of the functions which go from the torus to the gauge field. So in this case, we can say that if we stay with the U1 gauge field on the torus, that to each of these circles, we have an associated value of the so-called holonomy, I mean, of the integral of the gauge field along this line, which is a sort of Polyakov loop for this compactified direction. So now the point is, if you take two of these lines, I mean, for instance, this line and this other line, now in this case, if you consider the two lines going into opposite direction for a U1 field, you are effectively considering the flux going through the corresponding surface, okay, of the torus for a U1 gauge field. So this is related actually to the, since this is the flux, this is related to the to part of the topological charge, because the topological charge in this case is the total flux over the torus, which is quantized. But in this case, if you consider two holonomies going into opposite direction, it is like taking the circulation of the U1 gauge field in the two opposite directions. So it is effectively the flux of the magnetic fields along these lines. But again, I mean, the two holonomies have a non-trivial topology by themselves. I mean, they have, but then, I mean, the topology of the gauge configuration is associated to what is the value as you move this one holonomy from this point to the other. And you discover that the product of the two holonomies, I mean, if you make this this circle going around, of course it has to go to the since it is let me call this L, okay, L of x, so which is a sort of extension of the Polyakov loop. So this is L of x times this is point x along the torus, and this is y. So this is L dagger y, or just complex conjugate because it is 1. So you can see now that Lx times L dagger is the flux. The flux from x to y along the torus. Now you can play this exercise. I mean, imagine that this circle, you make a round over the torus and you reach x from the other side. Now what you learn again that since of course so if I consider the flux, so this is not the flux, sorry. This is not the flux, but it is the exponential of the flux, e to the I times the flux, okay, from x to y. Now, if you consider now the flux from x to x plus, let me say, 2 pi r, where r is the radius of the circle, okay, one of the radius of the torus. then it means that you are taking the logarithm of this is related to Lx times L dagger x plus 2 pi r, but by definition you are L dagger to x to plus 2 pi r is the same as x because we are going back. So this is the identity by periodic boundary conditions around the torus. So again, what you learn in this way is that phi, the flux must be quantized, okay, because e to the I, the flux must be, this is the flux from x to x plus 2 pi r. So it is actually the total flux going to the torus. And so in this way you learn that the total flux must be an integer multiple of 2 pi. Okay, so this is I was trying to interpret your idea about these non-trivial circles going around the torus in 2 dimensions. And actually, yes, I mean, you can use this idea to derive again the fact that the space of U1 gauge configurations as a non-trivial topology in this way. I mean, you can take the 2-point function in some sense of these holonomies, and it counts the flux between the 2 holonomies, and as you make a round, you get the total flux, and the total flux must be a multiple of 2 pi just because of the periodic boundary conditions in the other direction. So again, the topology of the configuration space that we find on the torus is in some sense related to the topology of the torus itself. So in this case, we made use of the fact that we had 2 circles. But actually, you discover that even if you go to the sphere, so to the spherical surface, you obtain the same quantization. So it is not strictly related to the topology of the torus, but to the fact that you are on a compactified space. And on the other hand, even on the torus, you could define a non-abelian gauge field where the topology is trivial because the gauge field, the gauge group is less trivial. So, I mean, the bottom line is that the topology of the gauge field configurations can be related to the topology of the manifold where you are defining the gauge configurations, but the link can be non-trivial and can be also ambiguous.
Okay, thank you. Thank you very much. It was very clear, and you actually also replied to the question that I was going to ask next, which was what happens if I consider a different topology for the lattice, such as sphere, or for example, if I have open boundary conditions. But yeah, you already said that, so I mean, thank you.
Yeah, on the sphere, I mean, you can play the game. On the sphere, you can play a different game to prove that the flux is quantized, and the game is that you take any circle and you take the circulation over the circle and say that the circulation of this circle of a mu dx mu is the flux, is the flux number 1, let me say, of the magnetic field in this across this surface. But it is also a minus the sorry, again, okay, no, this is correct, but it is also minus the flux going in the across the complement of the surface. Okay, so this is the flux 1 and this is the flux number 2. So you can ask, how is it possible that the two different fluxes are described with the same gauge potential? And the answer is that it seems that the sum of the two fluxes must be zero by definition. And indeed, it is so. I mean, it must be zero because the magnetic field has to, the flux of the magnetic field across a sphere must be zero because the magnetic field is the rotor of the gauge field potential. So the divergence of magnetic field is zero. But actually, you know that there is an escape to this, and the escape is that the circulation, the flux is zero but for an integer number, which is the Dirac quantization condition for the magnetic monopole. So again, you prove that because of this equivalence, if you require that this paradox is not visible to electric charges as they make a Aharonov-Bohm effect around this circle, then you discover that the flux must be just quantized. I mean, it is not that it must be zero strictly, but it is sufficient that it is quantized.
Thank you. It was very, very helpful.
Okay.
But sorry, in this case, the sphere is, I mean, it's immersed in R4 in a flat space. It's not our base manifold, right? I mean, otherwise, I was just thinking this is a curved base manifold. Can we do that? Can we do lattice simulations?
Yeah, we can do lattice simulations on the curved manifold. I mean, I will show you. I mean, for two-dimensional manifold, I will show you some results on curved manifold obtained on two-dimensional triangulations, which is interesting because of the topological freezing problem. So in principle, we can do simulations on curved manifolds. Okay, so, but the topology of the sphere actually is imposed every time, even on flat lattice, every time you impose that the gauge field vanishes at infinity. So in some sense, you are saying that the gauge field at infinity has one value, which is the gauge field strength at infinity has one value, which is just the trivial one. So in some sense, you are imposing by hand that the topology is the same as a sphere in that case. In some sense, I mean, of course, to have the topology of a sphere, you don't need that. You don't need to impose a metric. I mean that the curvature is the same as the sphere. You're just imposing that the topology is the same of the sphere, and what enters in the quantization is just the topology of the manifold, and not its metric. In any case, I mean, it is interesting that I will speak at some point also about simulations on the curved manifold.
Okay, thank you. But I mean, this is also the same one does with the torus, right? Because also the torus can be, I mean, it has a curvature, but I mean, if you build it by closing a sheet, I mean, a rectangle, or you can build it without curvature, just with a certain topology.
Exactly. Yeah.
Okay,
yeah.
okay. Thank you.
Sorry, again, I have been looking for that for a very long time. Can you like point to us some reference about lattice simulations on a sphere? But it's something that I've been looking for a long time.
So lattice simulations on a sphere, I'll give you maybe some reference. There are some papers by Rick Brouwer at MIT. They are working on simulations on a sphere. But let me find some reference. I mean, at some point in the next lectures, I will talk about simulations of the two-dimensional U1 gauge field on a triangulated torus. I mean, again, on a torus, but with a locally variable and also variable in time geometry. But I know there have been simulations on a sphere maybe Giuseppe, you know about these papers by Brouwer better.
Yes, I can put them in the chat maybe.
Okay, fine, thanks.
Yes, please. Thank you very much.
I have one small question.
Yeah.
About the way we can define a field strength tensor on a lattice by just multiplying plackets, I mean links around.
Mm-hmm.
Can we also define the dual field tensor if we find a way to put the epsilon tensor on the I mean, we can define an epsilon tensor like 1 minus Kronecker delta mu nu into 1 minus Kronecker delta mu rho. I mean, do you think we can put a dual stress tensor on a lattice?
Yes, of course you can.
Like how?
Well, in some sense, I mean, you can just if you're just considering the field strength, I mean, you can just trivially for each plaquette you have an association. I mean, you can associate the fermionic nu with e to the e g0 square times the mu nu. So basically, it is not an exact definition for a non-abelian gauge field, but you can take the imaginary part of the plaquette, okay, and at the first order in the lattice spacing, it gives you a possible definition of the field strength, okay, and you can play with that and obtain a definition of G dual. I mean, of the but trivially playing with the Levi-Civita tensor and so just switching the components.
Okay, you mean writing all the components of the field strength tensor and then just trivially writing the dual matrix of
yes.
Okay.
Now in the topological charge here, actually the game is played inside the trace. So you just take, instead of taking a plaquette, in this case you just take a non-trivial loop with 8 links, which explore all the 4 directions in space-time. I mean, this should be a non-trivial loop extending over all the 4 directions, okay, even if it's not clearly visible. And so as you take the trace, it at the first non-trivial order and the lattice spacing, it gives you GG dual directly. Okay. But you can play it also at the level of the single plaquette and obtain G dual, just G dual in this way. Of course, in this case, it is a relation which is valid at some order in A, so it is correct for smooth gauge fields.
Yes, okay. Thank you.
I also have a quick question more related to the first part of the lecture. That is, when you introduce these 2 renormalizing constants that are related, that you called it Z and M.
Yeah.
And so, like, I mean, if I understood correctly, it's the M constant that is more related to the ultraviolet divergences, because it's related to this contact, to the divergences, this contact term in the susceptibilities, while this Z1 is more related to the fact that
both of them actually are related to the ultraviolet fluctuations.
Because this, I mean, then maybe I'm not that sure that, because then the final question was like, is the cooling canceling both of them actually, or more this additive one? Yeah, because
the cooling is canceling both of them. Actually, I mean, in some sense, you are correct, because when you go to the continuum limit, I mean, while this z constant is finite, I mean, has some finite value which is goes from 0 to 1, okay, and it goes to 1 in the continuum limit.
Exactly.
The additive renormalization is actually divergent in the continuum.
Exactly. That's why I say, like, it looks to me, at least in my naive understanding, that the z constant will just have to go away, go into the continuum limit, because, for example,
yeah,
as you said, in this geometric definition, we don't have it at all, indeed. So, and the only thing, and it's not that the geometric definition doesn't have any ultraviolet divergences. So
exactly.
that's why.
So in some sense, Z is the good guy, and the bad guy.
Yeah. Okay. And that, so in some sense, it's true then that this cooling actually, it helps us, especially for dealing to this additive renormalization, more than to this is that one, or this is or is this wrong?
Well, it takes care of everything, but of course the most of the
effects that will be dumped out
from the additive part.
Okay. Yeah.
But you should in the if you look at these first determinations of the topological susceptibility by Di Vecchia, Fabricius, Rossi, and Veneziano, they were aware of the additive renormalization. Okay, so they computed it perturbatively and subtracted it from the topological susceptibility. But they didn't realize that there was also a multiplicative renormalization.
Okay.
So they obtain, if you look at this formula here, they just subtracted this additive renormalization. They didn't divide by z, and for this gluonic definition that I wrote here, the value of this multiplicative renormalization that you obtain for lattice spacing around 0.1 Fermi is of the order of 0.1. Okay, so it is not divergent, but it is between 0.1 and 0.2. So since it is squared, it means that it makes, if you don't divide by z squared, it makes a big factor. And
indeed,
if you look at the paper, the result of the paper was discouraging, because the result was that with the Veneziano mechanism was not working. Okay. Because they obtained a very small value for the topological susceptibility. So Z is a good guy, but you should
be aware of it.
not completely friendly. I mean.
Yeah.
Okay.